Great. So we're gonna self-serve. My hobby that's quote unquote outside of computing is technical theater. So I hope I can turn a microphone on and make it work. That'd be ideal. Although I do lighting, not sound. I feel like if anybody does technical theater, live sound is much harder. Lighting is much more like a script that you run. You get all the work done ahead of time, and then you just hit the button. Whereas live sound is very hard. But I am capable of turning on a piece of equipment, so we got that working. So thanks so much for coming, everyone. Today I want to talk about from COBOL to Cursor, which is a little odd because I don't work for Anthropic and I work for a company that kind of competes with Cursor, but that's okay. The alliteration works really well. And I've got the slides here if you want them. They're also posted on the SCaLE website, but you can go to brennan.fyi/COBOL if you want the slides. And yeah, we're gonna just kind of walk through a little bit of a history of how we got to where we are. And we're going to talk a lot about Amazing Grace, Admiral Grace Hopper. And so that kind of motivates this whole talk of bringing a language-first view to what we do as software developers. And I think it's a really interesting parallel to where we are today. But I think we've got to kind of lay that groundwork. First, as those that may or may not know, all of the amazing things that Amazing Grace contributed to our field. We'll walk kind of through that, and then like what that first revolution that she kind of led looked like in terms of shifting from very low-level arithmetic-only programming of computers to kind of a higher-level language. And then we'll talk about her least favorite phrase in the English language, which is the way we've always done it, and how there's always institutional resistance to change. And I think we're seeing a lot of that currently in software. And then we'll actually dive in and say, okay, so what now? What are like the practical implications of this, Brendan? It's a great looking slide deck, but like what do we do? Okay. So first let's talk about Admiral Hopper. I like to call her Admiral Hopper because A, that was her official title. Also, I'm from Annapolis, Maryland, so I'm a Navy fan, born and bred. It's kind of weird being from Annapolis when you didn't go to the Naval Academy because the Naval Academy becomes my like hometown college, right? Which like everybody's hometown college, you like get very, pumped up about. But then if I'm wearing like Naval Academy stuff, you all can see me. People kind of give me like a, I'm like, no. I was from Annapolis, I swear. I played backup nose tackle for the football team. No. Yeah, and so I alluded to it earlier, but Admiral Hopper's famously quoted as saying that the most dangerous phrase in the English language is "we've always done it that way." And I think that this is really true, and if you've ever heard any of the talks she's given, if you haven't, I highly recommend. There's a couple of great YouTube talks that have been recorded of her giving lectures on her very different way of looking at the world. And I think you will not be surprised if you've ever listened to those, that this was a kind of something she focused on a lot. And I think that, it's important because revolutions or even just like change in general always face this kind of reaction, right? This, hey, the status quo is working for us. We've always done it that way. It's not possible to do something another way. And that's just kind of the natural human default, right? Of, hey, we've always kind of done it this way. It generally works. Why mess with it? But I think we're going to talk a little bit about how she used this phrase to overcome a lot of resistance to change in her career. And hopefully that can, again, inform us what we can do today in resistance to that. And I think that's because disruptive change always looks very messy to incumbent players in anything, right? Like forget technology, forget even engineering as a general practice. Just in human nature, disruptive change, when you're the incumbent and you've been in an industry for a long time, or you've worked the same way for a long time, or you've thought of a religion for the same way for a long time, all of these things in human history, disruptive changes look very messy to the incumbent folks there. And that's something that I think I've seen over my career. So I've been in software since 2006. And I started off life in healthcare software, and I spent 10 years in breast imaging and breast cancer detection software, so a whole different world than what I'm in now. But that eventually led me to spend 5 years at a company called GitLab. That's an open source company. Saw that grow exponentially. And then left that to go to a couple other startups, and now I'm at a startup called KiloCode, which is, focused on an all-in-one AI agentic engineering platform. And so that's very different than the worlds I've been in before. But I think that, this current phase we're in, if we look at Grace Hopper's, 60-year career, shows us how this move towards language-first interfaces is going to just make computers and technology and programming and all of these things that we do much more accessible to many more people. And so that's a little bit about me. Let's talk a little bit more about Grace before we dive into what she did in her career. One of my favorite stories is when she was 7 years old. She took apart 7 different alarm clocks to try and figure out how they worked. Her mom was pretty upset with her about that. It's after my own heart because it's actually going away now. But I have this little scar here on my hand that's from taking apart a phone that wouldn't come apart. And so I hit it with a hammer, and the old plastic of a phone and a hammer had, an interesting reaction that left me literally scarred. She then went on to Yale, got her PhD from Yale, taught at Vassar, and didn't apply, but was asked to join the Navy when she was 37. And she was actually 15 pounds underweight for the Navy, but had to get like a special exemption to be admitted as an officer to the Navy. And then she retired from the Navy in 1966, and 2 months later was recalled for a 6-month additional post-retirement assignment that turned into lasting from 66 to 73. And during that time is when she was promoted to Admiral Hopper. And the first thing she worked on for the Navy was the Mark I computer, which was the first computer the Department of Defense ever had. And that was a computer that was programmed just in binary code. I think the Mark I was with punch cards. She would go on to be very famous for using the UNIVAC, which was actually programmed with magnetic tape. And then very famously, if you don't know, this picture here on the top is a logbook from the Mark I computer, which is actually in the Smithsonian now, because that little kind of yellowing area there is a moth that was blocking a contact in the computer. And like people like to say, oh, that's where the term bug came from. It's not. We were using the term bug in engineering before that, but Grace actually wrote first case of an actual bug in a computer, because the problem with that they were experiencing was this moth breaking contact. And so at that time, right, again, these machines were all programmed just in straight binary through a punch card, or like I said, or through magnetic tape. And there was no such thing as a programmer, right? There wasn't such a thing, right? That's a role that didn't exist because there was no portable, like readable programming language, right? There was not a concept of a programming language. And she actually ended up writing the first logbook for the UNIVAC because that's all she got handed when she worked on the Mark I, was just a logbook for this is how the computer works electrically, and good luck. And so that kind of moves us to this first revolution that she really was an advocate for. And it was both her technical and social mechanics of change, right? So in 1952, we talked about it's a nice stack of punch cards here. Again, technically the UNIVAC was published on magnetic tape, but that doesn't make for as good of an illustration. So you can see the punch cards here, right? And for those who haven't, I haven't actually ever programmed a computer with punch cards either. But you can see we've drawn like a line, a diagonal line, so that if they get out of order, right, I can put them back in the right order. Because if they're in the wrong order, you're going to have a bad day. And then there's also like other revisions that have happened, right? So like in the middle here, I can illustrate with this probably. like in the middle here, right? Oh, wow, that's way too big. There's additional lines. Oh, the eraser doesn't work. Okay. Well, now it's all just a mess. Yeah, I thought there'd be an eraser, but there's not. Okay. This is great. I love that for us. Okay. Oh, and it's still there. It's good. That's a fantastic feature. But these like other lines, smaller lines here, right, are revisions where like I had to repunch all of those cards and then put another revision in. So if you think Git was hard, that's real hard. Oh, I hit the wrong. Now I figured out how to kill it. Okay. Hold on. I have a plan. Just reset it up. Cool. I think I'm this way, yeah? Mouse, maybe? Oh, yeah. All right, now we're back. So that was the kind of the state of the art, right? Was programming like that. And Admiral Hopper had this idea of like, what if a machine could take human instructions and then translate that into machine code? Like, what if you could write something that was more like math or more like even English words, and then the computer could have a program that then figures out how to make that into binary code itself, right? This concept of a compiler was what she came up with. And she, was told very quickly, you can't do that because computers can't understand English. They only understand math. There's no possible way it'll ever happen. And so what does she do? Well, she builds a compiler, right? And she takes she builds it. It's called the A0 compiler. It was the first compiler ever made to take, at the time, what would become Flowmatic and then become COBOL, and turn it from these English words into compiled machine code. And it's kind of this, it's kind of interesting because that leads to this whole world that we're in today, right? Where we have this concept of machine code that we're writing directly, or maybe even assembly code, which is basically just machine code but in a different form, to COBOL, right, that Admiral Hopper ends up inventing, to now this, what are we doing now, right? I'm writing Next.js and I've got a node modules folder that's bigger than the whole project, and now we can have even LLMs do it. But the reality is these kind of filter into three areas, right? Machine code and assembly are very similar. Like I said, they're really, one is a binary representation, one is just a mnemonic representation of the same binary. But really everything after that, sometimes today we have these arguments about what's a high-level language and how low-level is a language. But really everything that's to the right is a high-level language in the sense that it's an abstraction built on top of the actual assembly or machine code that's going to be written. And again, the problem she faced at this point was she was told it's not possible. She actually wrote the compiler and no one used it besides her for 3 years. So she was the only programmer for like 3 years because she was the only one with the compiler that decided to use it. And she was told again over and over again that it wouldn't work. She said she kept pushing, right? She went past that A0 compiler, ended up making multiple versions of it, and ended up making COBOL from that. And people said, but then Grace, like everyone's going to be able to program. And she said, exactly, that's the plan. She wanted programming to be something that could happen closer to natural language, not just mathematical notation, right? Eventually there was another programming language called Fortran, which was much more focused on like the mathematical notation, right? The formula translation of the math that we're doing inside the computer versus COBOL, which was this common business language that was, hey, how can we turn that into English instead? Not just symbols, right? Words that like business people could read and understand. And I think that we see this shift over and over again, right? She said, what I was after was an English language programming to bring a whole other group of people into being able to use a computer easily. She continued to call for user user-friendly languages. And she was even quoted in a 60 Minutes interview in 1983 saying that was her like #1 goal as she started building this. And it's crazy to think that user-friendly was a word that she was thinking of in the 50s when the computer is in the entire taking up an entire room. Yeah. And I think this is something that we see kind of like shifting all the time, right? If we, she had this problem of going from, even assembly languages were at first kind of decried because they were abstracting away the zeros and ones to this mnemonics. Then, we move from assembly to COBOL and other high-level programming languages, and we get a lot of like, this isn't real programming. We see Python and we get to make fun of it a lot and call it not real programming because it's not object, it doesn't conform to the way we think of programming. And now I think we are seeing the same thing again where we're saying, oh, well, if you're just prompting an AI agent, well, that's not real programming either, right? And so we've seen this kind of, as we move up the stack and abstract away, the incumbents kind of say, well, it's the way we've always done it. And this is the best I could do, but she also would keep a clock on her wall that ran backwards. So whenever you came into her office, there was a clock running backwards, which I just flipped it and said the numbers are backwards, so sorry, but I had to get it to go counterclockwise. And it was a reminder when everybody came into her office that, hey, like, we've always done it that way is not going to be accepted in this office. And so let's talk a little bit about these modern parallels that we're seeing in the age of AI coding. Right. So here's two different internet things. One is Andrew Karpathy introducing the term vibe coding, probably one of the most famous tweets in our industry in the last couple of years. It's got, I think, I took this picture yesterday, 6.8 million views. And then there's our, Reddit, CS career questions. AI slop code is hiding all of the real code. And it used to be obvious when there was a problem. Oops, sorry, I did it again. It used to be obvious there was a problem, but now it's all AI slop, right? And so those are kind of the two different, we're seen as these like, there's only two different ways of thinking about it. It's either slop or it's, all vibes and don't ever read the code. My goal, if I can get my computer to function, is to tell you why it's not either of those things. Let's just do this, less complicated. And so why is there this disparity? Like what is causing this massive disparity between people that are theoretically in the same position as software engineers, but seeing the world of AI coding so differently? Well, one is AI is very good at being confidently wrong, right? It is never going to tell you you're wrong. It's always going to tell you you're absolutely right. And it's, if you just trust it innately, you're going to get burned by it, right? You're going to have major issues, right? I don't know what happened. I vibe coded this whole presentation, and now look at me. I started talking bad about LLMs, and they got me. I don't know what happened. I'm still connected to the HDMI. It's my goal. Well, so I unplugged it. It didn't react. Yeah, I think so, maybe.
It thinks there's a signal.
I hit the table. I don't know what I did.
Did you say something mean to the table?
No.
Wait a second. Where are you hooked up?
Right here.
HDMI. No, it's solidly in there. Is your computer maybe just stopped sending a signal?
No, it's like, watch it. You can see it change.
So it thinks it's sending a signal. We may be impaired here. I'll see if I can get some.
Okay, well, I'll keep talking. Hopefully we can get it back for at least the demo, maybe. Okay, I'll keep talking. We don't need the slides so much for me to talk, but hopefully we can get it back for the demo. So yeah, where were we? We were talking about how it can be confidently wrong, right? And I think this is something that's interesting because it's not that different than, you know, a junior developer, right, who's very well read and maybe never really implemented code in production before and can be very confidently wrong, right? And just like you wouldn't, you know, necessarily trust that junior developer to, you know, go and just push code straight to production, you shouldn't do the same for AI, right? Because you'd have to trust but verify, right? Read the code, understand the changes that are being made, and we shouldn't hold our AI agents to a different standard. It should be the same standard we hold any contributor to. And then the next would be that it's like, you know, the next argument against would say, oh, well, we're making engineering a commodity. If we make engineering a commodity, then we're all out of a job, right? And again, I think hopefully we've seen through these multiple abstraction layers that have come into software engineering throughout time, you know, it didn't reduce the need for programmers in any of those abstraction layers. It increased the need, right? Every time we've, you know, solved part of the stack and brought ourselves up to a higher level, we've been able to do much more incredible things, right? Like we wouldn't probably have, you know, half the technology we have today if we still had to be, you know, programming everything through a punch card. So I think the revolution, again, can be scary when it's happening, but I don't think that we've yet seen, and I could be wrong, you could come back to me in 5 years and tell me how wrong I was, but I don't think we've yet seen a revolution where we've been able to make a complete commodity out of engineering just by moving up the stack. And then the next argument would probably be that you can't trust it for anything important. You know, if you, you know, like if you're going to have AI code something and it's production grade or it's really important, you know, what is the you know, the reality of being able to then ship that into production? Can I really trust it to ship it in production? And I think, again, if we think through this history of through, you know, moving up the stack, it's like when you run something through your compiler, do you read the machine code that comes out of that today, right? Like, do you go and inspect that and read it? Do you look at like the, you know, just-in-time output of the runtime that you're running and really inspect the V8 engine, the JavaScript that you're running, and look at how it's actually interpreting your code? And then again, to like the silly example I made of myself and bringing in lots of node modules, it's like we're shipping lots of code we haven't read. If it's in, you know, a dependency, right? We're not reading every line of code in a dependency. And so I think the question is not necessarily like, can I or can I not trust this? It's not kind of that black and white of a question. The question is like, where do I draw the line? What can I trust? And you know, that line's always moved, but that line is always the important thing that we had to understand. And then, okay, so I'm just trying to buy some time for the demo. So again, another thing that I wanted to talk about is when Admiral Grace was interviewed in 1983 on 60 Minutes, which again is available on YouTube if you want to take a look at it. It was interesting because they said to her, like, oh, well, you've seen all this advancement since the 50s, and, you know, do you think we're really, you know, is the computer revolution over, or, you know, have we reached the peak? And her statement in 83 was that, no, we're at the Model T. Yeah, go ahead, do what you need to do. And so it's interesting to me that her assessment of the time between, that was the button I hit, didn't I? There you go. Thank you. Hey, thank you. Now we know why I hit the table. We know. Yeah, so it's interesting to me that her assessment of the progress made from, you know, the early 50s when she was involved to 1983 when she was, of course, retired was like, okay, that got us to the Model T, right? And that was surprising to Morley Schaefer, who was interviewing her, but I don't think it's surprising to any of us that have now seen what's happened from 1983 until now. And I think that that's interesting to again think about in the days in the age of AI, where the models are the worst that they're ever going to be, like today. Our understanding of how to work with it is the worst it's ever going to be today, and we've seen that all of these changes in technology adjust over time, and we learn how to adapt and make it work for us. Great. So just in time for the demos, so what now, Brendan, right? So how do we, if I'm sitting in the audience, I'm a software engineer, I've been a software engineer for a long time, how can I work with AI in a way that doesn't make me, doesn't have those problems that we talked about, which is what can I trust to ship? How can I avoid it being confidently wrong? How can I make sure that it's actually a partner in engineering and not making it harder for me? And so there's a couple of things. First of all, I think you have to be very explicit, right? Like just, again, if you're working with a junior engineer who's never seen your code base before, and you just tell them, hey, there's a bug with the button on the table, you hit it and no one knows what you did, that doesn't give them very much context. If instead you say, well, the button's attached to some sort of HDMI splitter below, and if you hit the button, it's not obvious that you're now looking at something else, right? Like that now gives them enough information to solve the problem, right? And so being very explicit, right? The ongoing joke on the internet is like, make no mistakes. I mean, that's helpful, it's a good idea, but that does not a good prompt to make. And then also I think providing context. So we've seen a lot written about context engineering, providing to the large language models the patterns that exist in the code base already, examples of what you want to be, and building kind of good habits around keeping the context to be just about the thing that you're working on and how you want it to be solved is really critical. And then setting the right constraints, right? So it's like any new tool, you have to build an intuition for how is this tool going to work with me? When do I need to stop, start, restart, or push it further? And so that kind of brings me to like this general concept of all of this, right? From Admiral Grace's concept of COBOL to today, software engineering's always been about expressing the right intent of the engineer, right? And that's been true since, for any programming language. And it's going to continue to be true, if not even more true, in the age of AI, because expressing very clear intent and having a clear fundamental understanding of what that intent is going to be very critical. And so how do we actually apply that in practice? There's been a lot of different frameworks out there. I don't claim to have the like monopoly on frameworks, but the one that I keep coming back to is this RPI framework that folks have been writing about called Research, Plan, and Implement. And so this kind of solves those same three problems we were talking about before, right? If I first research and spend a lot of time understanding the scope of the problem and where the problem's going to get fixed, I can then plan a lot better, right? I can then build those patterns and examples in to my plan, and then when I'm implementing, it helps me build that intuition, and I've already got a plan in place that's going to be successful. So that's what I kind of want to demo here. First let's talk about research specifically. The idea of research is understanding the system that's in place, finding the right structure for what we're going to be building, and then understanding, hey, I as a human am going to ask it to do some research, but then I'm going to review the results. So the example that I'm going to give in this demo is something that I actually encountered yesterday when I was on my way to the airport here. Has anyone heard of OpenClaw in the room? Okay, a few people have heard of OpenClaw. I've been playing with it a lot. Kilo even has a product out now for hosting it. But one thing I wanted to do is I built a thing called Pinch Bench. So the idea is like, how can we benchmark this like most wild of AI agents, OpenClaw? And so I created a benchmark that has a bunch of tasks that try to mirror like what people are actually using OpenClaw for, and then let's run that against all the various models and get a score. And mostly it was for fun. But then I'm literally on my way to BWI. I'm from the East Coast, didn't mention that. And this tweet comes out yesterday. at 7 a.m. our time here, but I was in the airport in Baltimore, and it's Peter, the creator of OpenClaw, and he tweets, "That's a really interesting benchmark I just found, pinch bench." So this caused quite the spike in traffic. He also DM'd me and said, now that he works for OpenAI, he DM'd me and said, hey, why is GPT 5.4 not in there yet? And I was like, okay, yep, I'll fix that. So I had this need to go and implement, because I had just run the benchmark myself. I had built some kind of virtual machines, a little bit of orchestration. I hadn't really planned for this thing to take off, right? It was kind of just a fun side project. But like I said, it did take off when someone, when Peter took notice. So now I had to kind of say, okay, how can I automate this whole system and bring it, like orchestrate it? And so let's talk about how I kind of did that. So if we're and let's just do a little demo here of pinch bench. So again, the idea is relatively simple, right? It's inspired by the simplest benchmarks I could find out there. And each one of these is a set of tasks that get judged. Some of them are automated judged, some of them are LLM judged. Suffice it to say, it's like a lot of Python getting run to orchestrate OpenClaw against it. And you get a lot of like cool graphs, right? Like cost versus accuracy. Love it, it's great. But now I need to automate it because it had just been my laptop running a bunch of Vultr instances itself. So step one would be to research, right? And so, one key I think is to think about these modes differently. And so that it happens to be Kilo. There's lots of other iterations of this, but in Kilo we think of it through these different modes, and we have code mode, which is like the typical demo you see of like spitting out a bunch of code at you. But that's not what I want to do. I want to plan this out better first. So I'm going to go to ask mode, and I'm going to say, I want to create a project to automate the generation of the new benchmarks. I'm in the benchmark repo here, right? This is where all the tasks live, right? Like the weather task, like what the expected behavior should be, how it's supposed to work. And I'm asking the agent to say, based on this, what would I need to understand in order to create an orchestration layer on top of this, right? So this is where I want to research it. And we can see the agent here in ask mode actually cannot write any files. And all I can do is read. It's read only. And okay, so it created this. I have understanding now. And let's just pull this into a markdown. Oh, it's still writing it. Almost done. Live demo. It's going to be with me. It wasn't with me earlier with the projector, but it's going to be with me this time. All right, so it can't write this file, but I can. I'm still thinking. That's a good question, yeah. I don't know. I wonder if I can switch to light mode, and it'll help. There we go, okay. That'll help a little bit. Okay, great. So it created this file. Oops, that's not what I want to copy. I want to copy this. No. I can. I'm trying to get it up in a preview so that we can see it better. Yep. Just give me 1 second. Just copying all of it. Okay. I'm going to copy all of it so we can see it a lot bigger. Okay. Yeah. So again, it's now given me this entire concept of, and I didn't save it as markdown, or it didn't come over as markdown quite right, but it has like a whole graph of how all of these things work together, all of the requirements that I would need to parse the markdown, all the things that I'm going to need to create and manage agents, right? So this research in real life, I would read and understand and make sure that we really are, all of the flow charts and everything are exactly what I would expect based on my knowledge of the code base. And I'm going to ask it to write it to a file because I think it'll be better. Oh man, it's so big I can't even do it. Try to be nice to our AI overlords and say please every now and again. Just in case. Just think it'll be easier for us to see the diagrams if I can get it to write it. I can also go, the thing to always have in the live demo is a cooked turkey. So I can check out my branch cooked turkey. And in that branch, I have my benchmark automation guide. All right, so here we can see it's got these diagrams of what the input layer is going to look like, what the orchestration layer will look like, what components we're going to need to build, how task management works, right? So again, I'm going to go through all of this as the human and make sure this research matches my understanding of the system. And only after that, very explicit time spent in research and in reading that, am I going to then move on to plan, right? And so, again, I'm going to have the plan mode output the exact steps it's going to take, include how we're going to test it, be very explicit about how I want it to build it, and its output is going to, again, not be code, but be a human-reviewed plan file. So if I go back to VS Code, I've got my guide, and I can say in this new repository where I don't have anything yet, I can say, oh, I do have something because I'm on cooked turkey. Or I don't have anything yet. I can say, hey, I want to plan the automated benchmark tool that can run live in the cloud. Come up with 3 to 5 different architectures so that we can talk through the implementation options. This is another real key when working with AI is you can ask it to give you options, and then that actually can help you think through some of the issues there. Below is the detail from a benchmark repository of how it works in one machine. So I'm going to put in that whole document we just got. And this is actually going to take it much longer. So we are going to go right to the cooked turkey, which is why I was on it. Because the plan file that comes out of there then is going to be a very detailed architecture about what I'm going to need. Like what are the secrets that we're going to need in order to run it. And then it's going to give me different architecture options, right? I could use modal.com. So this is all Python, so it thought, hey, well, modal runs Python well, right? What if you did that? And it shows you what an implementation would look like. Gives me pros and cons, right? Very easy to implement, no idle cost, con and vendor lock-in, right? Like I'm going to be building against their API. Estimated effort 1 to 2 days. Little does it know I'm going to make it do it after this talk in the next 10 minutes. AWS step functions, fly machines, fly.io, GitHub Actions. And then the nice thing is it actually gives me a comparison, right? So I can actually think through, what are the criteria that I need to think about before I execute this plan, and how do each of the architectures weigh into that. Now, of course, this still is coming out of the AI, right? So I'm still going to have to, as a human, read this, understand it, make sure that I agree with its assumptions. But again, it gives me things that maybe I haven't thought about, right? Like, what about retry and error handling? Again, I wrote this code. There's going to be a lot of that, right? So like, how is that going to work? And so only after I, again, read through this plan and choose from the architecture am I then going to go and say, okay, now I want you to go ahead and implement it. And we're not going to spend time on that from the demo perspective, because of course, again, that's going to take a lot of time. But the key about doing those 2 steps ahead of time of the research and the planning is now when I go to implement, it's going to be very low context, right? The context for that agent is only going to be those things that I really want it to go do, and I've already made a lot of the decisions for it, rather than letting it kind of just decide by the roll of the dice what decisions it's going to make, right? Again, we saw the different architectures that it came up with. If I use that same model and said implement it without a plan, then it would have just chosen one of those at random, right? Like it wouldn't have necessarily thought through those different trade-offs. And that allows me then to review every change and commit frequently. And this human review at that research and planning stage is the high leverage of your time, right? That's the engineering portion of the software engineering lifecycle, not the actual typing every letter in, or just like we would have to punch every card in before. And Dex Horthy, who works for a company called HumanLayer, has this great quote that I love, which is AI cannot replace your thinking. It only amplifies the thinking you've already done or the lack thereof, right? So if you haven't done a lot of thinking beforehand, it will be great at amplifying that. But if you've done a lot of thinking beforehand, you can actually amplify that very quickly. And so that's a link to the YouTube video where he talks about this, and he talks about I had 3 steps for you. He's got 12-factor AI agents for you if you want to really dive deep. And so, right, I think because of that, these old disciplines, these disciplines of engineering and making strong decisions and thinking through architecture, those are actually going to matter more in the age of AI, not less, right? If writing code is cheap now, which I think it is, right? We can all kind of agree with that. Every demo of something writing code really quickly has shown us that. Software is not, right? Like engineered software is not cheap, and it's not going to be anytime soon, because the engineering habits that we have around like it being an expensive thing to write the code are gone. You can now just build things, right? And so with that constraint gone, it doesn't mean that all of the constraints of engineering are gone. It just means that those only come to matter even more. And then, so just some 3 further reading if you want to. Path.kilo.ai is a pragmatic guide for engineers and leaders that I'm writing and open sourcing. It has a lot of the links that I used in the research for this talk there. If you haven't looked at agents.md yet, I highly recommend it. Finally, all of us crazy AI vendors are hopefully standardizing around a way to instruct and give the agents the right context to begin with, and that's going to be through agents.md. And then lastly, Simon Williamson, if you haven't read his thoughts on agentic engineering, I think he's probably the best writer on it that exists today. And then I can be found on the internet anywhere at O'Leary Crew. And I would just close by saying, like, I think that we owe Amazing Grace a lot. I've got on my T-shirt here, Ada and Jean and Grace and Margaret, which is the Grace is Grace Hopper, Margaret's Margaret Hamilton, Ada Lovelace, obviously. She didn't write the compiler so that we could stop learning. She wrote the compiler so that more people could learn. She wrote it so that we could learn different things, so that we could do higher level things, so we could do more valuable things. And so I think if we think about AI agents as another iteration of that, it can change your perspective on how to use them and where we're at, right? And if we've got this kind of progression towards natural language, I think that's exactly what Admiral Hopper was going for. And so, thank you very much. You can find me anywhere on the internet, O'Leary Crew, and happy to take any questions. I hit the button again. Happy to take any questions. Yes?
So what did the history of actual COBOL look like? What was the thinking that Grace Hopper had?
Yeah.
Going from just having a good assembler.
Yes.
To having a higher language.
Yeah, so that's a great question. First of all, there's a really great map. I will tweet it after the talk, where someone has mapped out the full lineage of every programming language with each other. It's like 19 pages wide. And actually, if you print it and post it on your wall, they then post your picture of it on your wall back. And so the interesting thing there is I think Fortran technically predates COBOL. And she really thought that it was too mathematical, right? She wanted computing to be accessible to more than just the mathematically gifted, right? PhDs. And so COBOL is a common operating business language, something, don't quote, operating language, right? And so it was really about expressing this, business needs, which for her at the time was the Navy, but then later other businesses. And so it was about like using English to expand who can understand what a program's doing, right? And so Fortran's obviously much more formula-based. And so it was really about natural language and bringing natural language to it. Does that answer? Sorry, keep going.
What was her thinking when she knew that she wanted to structure that. How did she go from a series of developer operating steps?
Right. That's a good question. Yeah, I think she invented this idea of like we could have some middleware program that compiles it down to assembly, right? And so I think her goal was to make that, and I think it was just, I don't know the exact steps, how she got to the syntax that she chose, but it was if I can create a syntax and then turn that into machine language with program A, compiler, and then run it on the computer, then a lot more people would be able to be. I think she was working with a lot of folks, a lot of very smart engineers who weren't necessarily electrical engineers in the Navy, and she wanted to bring their knowledge into what they were able to get done, right? So they were computing a lot of nuclear engineering things at the time, of course, for World War II. And so I think she wanted to bring that knowledge into the computing space and make it easier for people to express themselves who maybe their first discipline was not electrical engineering or math. Yes?
I know 3 out of the 4 names on your T-shirt.
Okay. Jean, she is, that always gets me. She worked for NASA. Gosh, what's her last name? What's that? Simon, yes, yeah. Worked for NASA in the computing division. Yeah. Yeah, go ahead.
Just quickly to answer your question, a little more about COBOL, if you don't mind.
Yeah, no, please. I don't know. I know very little about COBOL.
There's a really good podcast called Advent of Computing, and the host did a really, really excellent, hour-long episode on the history of COBOL, of how it was developed, because it's actually based on a language she wrote slightly before that.
Yes.
And then the committee kind of took it, and so he's like, you don't have to blame Grace for COBOL, because he has.
That's true. It was Flowmatic was actually what she wrote. Yeah.
But it's a really amazing episode.
Thank you. I think you had a question here. Yeah.
How do you consider your privacy when you're using these AI models? And then how do you keep yourself safe when you're using OpenClaw?
Two very hard questions, one harder than the next. So how do you consider, what do you consider privacy? I think I'm very excited about all the work that's being done in open weight models because I think that's going to enable us to not rely on, a duopoly of companies to provide us with AI inference. I have been with Kilo now since April of last year. And last year it was all about Opus and how great that is. I think this year is going to be the year that open weight models catch up and pass, or at least catch up with the premier labs. I think that's a really great way to run your own inference, right? I have a Mac Studio at home and I can run pretty serious models on it now, and I think that's only going to get better, right? I think Quen just came out with, can't remember what it's called, but I saw someone demoing it on a phone, running the model on a phone CPU and GPU. So I think if privacy is a major concern, I think there's a lot of options out there for running your own inference. I think that's the only way to guarantee it. I think there's also a lot of inference providers that make guarantees to you, right? If you want to trust them about, if you're using the API, then you're not going to be used in training data. If you're just logging on and not even logging on to a chat app on the internet, I would assume you are going to be in the training data. And then second, how do you keep yourself safe with OpenClaw? That's a great question. I actually wrote a whole blog. If you go to blog.kilo.ai and search for Claude, you'll find it. When I first encountered OpenClaw, I installed it directly on my Mac because that's what everybody was doing. And then I actually went to our company. We're located all over the world, but kind of half of us are in Europe, and we were going to Spain for a company offsite, and it was like deleting emails of mine that I needed, and for my wife, hey, can you fill out this form for school? And yeah, sure. And so I took it off immediately, right? Because I was getting really worried. But then I've reinstalled it. I reinstalled it on a VPS, and now actually I run it on a computer, a Linux computer in my house. But what I did is I have this same model, right? We talked about this model of treating it like a junior engineer. It's you wouldn't hire a junior engineer or an intern or even a personal assistant and just give them your passwords for everything the next day. You'd give them their own account. So I actually have, if we go to github.com/scuttlebot, which is the name of my OpenClaw, this is actually my OpenClaw agent's GitHub account. And so it has full access to this GitHub account. And then this GitHub account is a developer, not a maintainer on my repositories, right? And you can see it gets a little active. Again, yesterday, I was trying very quickly to respond to Peter's tweet. And so he had a lot of contributions yesterday. But this way, I get to treat everything that the OpenClaw agent does as I would any junior developer, and it sends me PRs and I review them. And so I think this is kind of the way that I found. And again, I wrote a whole blog on the details of how I did this. Again, that's trading off some things, right? It can't read my iMessages for me and respond to them and right? There's this convenience versus security or trade-off, and I think that we're still learning what the right line is going to be there for sure. Yes?
Have you done any work converting old COBOL code with large language models?
It's pretty good at it, actually. There's actually a paper. Someone wrote a paper on it. I don't have it off the top of my head, but somebody wrote a paper on it. I think it's pretty good. I don't know that I would just go into a bank tomorrow and convert all the COBOL to Next.js. Again, I think it's pretty solid, right? But I don't think I would trust it to just do it. But the semantical differences between languages is something that large language models are actually pretty good at reasoning against. Well, not reasoning, but reasoning against. Yes.
I guess from my personal use, I'm seeing more of a purpose to test-driven development. The tests are deterministic.
Mm-hmm.
That's the one thing kind of so how do you see that?
Yeah, it's a great question. Yeah, so I talked about this RPI methodology. There's a lot of other methodologies out there, and spec-driven development is another one that you'll hear people talk about a lot. I've actually got this section on trends and patterns on this path.kilo.ai where I talk about a lot more of them. I think that agents are really good at running tests, and so if you're already kind of in this test-driven development methodology, I've seen a lot of people have success of I wrote the test and then had it write the code. I think that assumes that you're already really good at tests, which maybe everybody in here is really great at tests, and it's just me. But I'm not really great at tests. And so that's why I didn't choose that as the thing to talk about in this talk. I think RPI applies, even if you were just saying, hey, I want to do it test-driven, it's you'd still research, what should the test be? Plan, hey, what is the structure of the test and how what's that output going to be expected? And then implement, okay, now the tests exist, let's implement against those tests. So I think that's why I chose that for the talk, but there's a lot more information out there on folks that are doing spec-driven development and test-driven development with AI. Yes, go ahead.
You had said open weights could be positive for privacy concerns.
Mm-hmm.
Do you think that's enough? As opposed to open source or maybe open training data?
I would love it if it was open source and the training data was open and repeatable. I think if it's the beauty of open weight is you can then run it on your own hardware, and you know that nothing's going outside of your hardware, right? I think it'd be better if we had the training data open as well, but I think that open weight gets us a big chunk of the way there, right? Like my concern from a privacy perspective would be the code that I'm writing, the code that I'm researching and planning against, is that then going back in to be fed into the model's training data? If I'm running it on my own hardware, I can guarantee that that's not true. And so that's why I think open weight gets you the 80-20, I think, is open weight. Of course, I'd rather it be open source. I've worked for open source companies for a long time. But I think open weights does the 80-20 at least. Awesome. All right, well, I'll be around a little bit longer if anybody has anything else, but thank you all so much. Thanks for bearing through my major HDMI issues. Appreciate it.
45. Okay, testing.
Good afternoon, everyone. We're going to go ahead and get started. This afternoon we have Dave Neary. One second, phone locked. Dave Neary leads the developer relations team at Ampere Computing, promoting the adoption of ARM64 cloud native processors. Please take it away.
Thank you very much. Thank you for that introduction. And this is a new talk, so I'm going to be trying some stuff out. I'm hoping this will be a little bit interactive. I also just recently, and as anybody who saw my presentation yesterday knows, I talked about it a bit, I recently got progressive lenses, so I'm still trying to figure out, I'm in the acclimatization period for anybody who has progressives, like sometimes I take them off, sometimes it's funky, but anyway, I'll give it a go like this. And if you see me looking around, I'm just trying to find that spot where the magnification is right. Okay, so today's talk, you don't care who I am, you care what I have to say, right? So what I'm going to talk to you a little bit about what developers should know about computer architecture. As a rough agenda, we're going to go over why developers should know a little bit about hardware design in the first place, like why is this relevant? Doesn't the compiler take care of everything? We're going to talk about memory and disk latencies and how that can affect the performance of programs. We've got some examples in there. We're going to talk about the way modern CPU pipelines work. If you're familiar with that already, then you're probably not going to learn anything because I'm going to come at it from pretty high level. My goal is to target high-level programmers who have never really thought about how the hardware works. And then we're going to have a section on developing for parallelism. What does that mean? How does that change what you need to do? What are some of the pitfalls that you can fall into in terms of kind of destroying the performance of things rather than taking advantage of multiple cores or multiple CPUs? We're going to summarize with some lessons learned. So let's get started. Okay, first off, why should developers care about what the hardware is doing? Doesn't the compiler and the high-level language, don't they already take care of that? At least that was my perception. You know, compilers are pretty good at optimizing code these days. So why do I need to know, you know, how memory layout works or how the CPU pipeline works? Well, modern compilers are amazing. They can do lots of work that you don't explicitly ask for. Like they can unroll loops, they can remove branches that they can move to branchless instructions. They routinely reorder or change instructions so that you can, so that as long as it doesn't affect the output, so that you're more optimized in how you use the CPU pipeline. You can even automatically vectorize code. So the compiler will detect if you have SIMD modules, it will detect, oh, we've got the opportunity to process this vector of data 4 items at a time, and it'll do that for you. You never need to know how to do SIMD. SIMD is single input, multiple data. So it's a way to, it's vectorized, so any GPU program is going to use SIMD programming. You're basically processing vectors of data item by item in chunks. So modern compilers are amazing, but they don't do everything for you. They don't own your algorithm. They don't own your data structures. For any Angelinos here, this is the St. Francis Dam. So I don't know if any of you know this story. You do? Okay, so the St. Francis Dam, it's up one of the canyons near here. It was designed and built by William Mulholland, eternalized in Mulholland Drive in the Mulholland Dam, which was another dam built by this Irish guy. So sorry about that. So it was a British-Irish self-taught architect who was very active in designing the water system of Los Angeles. This dam was built in 1927-28. And the dam didn't really take account of the substrate, right? The dam was not designed with an understanding of how the rock underneath was made up. There were several tests, and Mulholland, to his credit, took absolute full responsibility for it. It ended his career when this dam collapsed. It killed 431 Angelinos. It collapsed in 1928, right before the Great Depression. Part of the valley in which the dam was built was schist, which moved a little bit under the pressure of the concrete, caused cracks during the construction. It passed an inspection 12 hours before it collapsed. So this is just a cautionary tale. If you don't take account of what's happening underneath what you're building, you can have bad results. Hopefully this is not going to happen with your code, right? But you never know. So, algorithms, data structures, deployment choices, these matter for your application's performance. So it's important that you understand how what you're doing at the high level translates into what happens at the low level, particularly if it's going to dramatically impact performance. In general, you want to swim with the current. In this presentation, we're going to cover a number of hardware behaviors that might be invisible to you as an application developer, but they can be the silent performance killer for your application. They can cause your code to run 10 times, 100 times, 1,000 times slower. By gaining awareness of the underlying behavior, you can just write more optimal code. You can take advantage of the hardware and just make it easy for the CPU to help you do what you want to do. So we're going to cover 3 big topics: memory, locality, and data coherence, data access patterns, modern CPU pipelines, and coding for parallelism in multi-core or multi-host environments. Okay, so let's get started. Before we get into the content, I do have to talk a little bit about Ampere, but it's only just an introduction to show what a modern CPU looks like. When I talk about coding for the cloud or coding for a modern CPU, what do I mean? This is the Ampere 1M. It's our latest product. It's up to 192 cores at up to 3.6 gigahertz. You get, on each core, you get 16K of L1 instruction cache and 64K of L1 data cache. We'll talk about those a little bit later. You get 2 megabytes of L2 cache per core, 64 megabytes of system level cache. That's cache that's shared across all of the cores on a single socket, and 12 channels of DDR5 memory, up to 1.5 terabytes of RAM. And we also have some vector units per core, 2 128-bit vector units for SIMD calculations. Right, so this is what I'm going to use. When I do latency figures here, I'm going to be citing the figures for Ampere. It's just because I know what they are, for a start. But this is, like, when we're talking about modern CPUs and when we're talking about coding for parallelism, this is what you get in the cloud these days. I do not know what the TDP is. I do not know what the power consumption is, but I know that we're very, very competitive in power consumption because that's kind of the core. We're an ARM64 CPU, so that's kind of one of the core reasons why we believe ARM64 CPUs are kind of. The question was, what's the power consumption of that CPU? Power consumption is like power per core, but even power per socket. We're very, very competitive with anything out there. It's much lower than x86. And that's one of the reasons why we think this is kind of the future of the data center, is if you put a CPU that big, that's an x86 CPU, you have to account for heat, you have to account for cooling, you have to account for airflow or water flow through the server. You're putting fewer cores per rack because you have to leave empty spots for heat. I don't know if anybody have worked in a data center, but like the classic cold aisle, hot aisle, you need to account for the airflow that's going through these things. With Ampere CPUs, you don't have that problem, so you fill up your racks. You can have 42 servers in a rack, standard size rack, which means that you've got more cores in your data center, which means you're building fewer data centers, which means you're putting less pressure on the grid, which means there's a whole bunch of good stuff for CSPs, but it's also good for customers because your CSPs are renting you those cores cheaper. Anyway, he asked. I wasn't going to go into the sales pitch, but there you go. That's why we think ARM64 CPUs for the cloud are really important for the future. Let's get talking about some of the things that you need to know as a developer. So we're going to start with memory and disk latencies. So to make this a little bit more concrete, something that you can identify with, I said to myself, how can I turn nanoseconds, microseconds, and milliseconds into something that's meaningful to this audience? So since we're in Pasadena, I'm going to take a local landmark as a reference. We're going to take the Rose Bowl, the Pasadena Rose Bowl, and we're going to start from the 50-yard line. And to illustrate time taken, I'm going to use light time, right? So a meter and so one light second is 3 billion meters, right? So it's 3 billion meters per second, 1 light second. We're going to take access time to different levels of cache or memory as light distance. And I'm going to ask you all to guess how far light can travel and the time it takes for data to load. And I'm going to give you a freebie. If you are accessing layer 1 cache, you can barely see the red dot in the middle there because loads from L1 cache are fast. They're about 1 nanosecond. So 1 nanosecond is 1/3 of a meter, 30 centimeters, right? About a foot. So you're still basically at the halfway line. Maybe if we're doing this when there's a football match going, and the ball is placed on the halfway line, you're about like you can just about get outside the football, right? That's the kind of scale we're looking for. But remember, you only get 16K of instruction cache and 64K of data cache. So iCache is where your program lives. Data cache is where data structures can live that are accessed. So you've got small amounts of that data. What that means is that if your data that you care about on the fast path of your application is less than 64K, access to that data is super fast, but you don't have a lot of it. Okay? Now, moving from L1 cache to L2 cache, how far, who wants to guess how far we get away from midfield? The sideline? Okay, anybody else want to guess? Middle of the city of Pasadena? Stadium height? Okay, so outside the field, more than 100 yards, a 20-yard line I heard. Well, so those are all good guesses, but they're a little bit pessimistic. We actually get about, so it's 3 to 10 nanoseconds, on average about 5 nanoseconds. So we're talking about 5 feet, 2 meters, 2 yards, right? So light has now traveled between 1 and 3 yards, so let's say 2 yards. So you're surrounding your center and your defensive linesman, maybe, right? It's not too far, but your arm's reach from the ball. So even though like layer 1 to layer 2 is slower, it's 5 times as slow, and you now have 2 megabytes per core. So if you can fit your hot path data in 2 megabytes, you're guaranteeing that your access time is going to be still pretty fast, right? Next up, we've got the system level cache. This is a shared cache by all of the cores. So you've got some bus latency, right? Because you've got mesh interconnect between all of these cores with their local memory. But if you're going to the system level cache, it's a little bit slower. Anybody want to guess how many times more slower? Twice as slow, 20 nanoseconds. 5 times as slow, so that would be 25, 30 nanoseconds. And it ends up being somewhere between 10 and 40 nanoseconds, so about 30 nanoseconds is the average. At this point, you've got, so we're gone past 10 yards away from, we're now, it's about, I think, 15 yards, give or take, 12, 15 yards. So we're now past the 40-yard line in either direction. So again, thinking about Ampere 1s, you've got 64 megabytes of this per socket. So that's shared across up to 192 cores. So you don't get a lot per core, but you also have the ability to define policy so that which cores get access and which cores get fast access to the system level cache, and you can deny access to the system level cache to certain cores. So it's you do have ways to tune this, but you've got a lot more data. This is still, I think, pretty fast, right? Okay, so now we're going to go to the next one, which is SD-RAM, right? Are we still on the field? Hold on. This is skipping a slide. Why do I not have an SD-RAM slide? Yeah, but with SD-RAM, you're about 80 yards. So SD-RAM, you're talking about 100 to 150 nanoseconds. So it's about 5 times slower than this. So where we're 15 yards, 5 times, we're about 75 yards. You're in the end zones potentially, certainly sideline to sideline. I've kind of buried the lead. Now if I now go to the next fastest storage medium, it's local attached NVMe solid state disks, right? Okay, at this point, right, let's say we've got 100 yards for SD-RAM. How far away from the center field are we with NVMe? NVMe is basically storage, is basically RAM, right? It's a little bit more than that. It's 20 to 120 microseconds, so we've changed order of magnitude. We've gone from nanoseconds, 120 to 150 nanoseconds. We've now gone to 20 to 120 microseconds. Now, we've got a lot more of it. We've got hundreds of gigabytes of this stuff. If you have money and bought some before the prices went through the roof. That's also true of SG-RAM, by the way. But latency times for fast NVMe disks are in the tens of microseconds. So in terms of landmarks from here, in the optimistic case, you can get to the JPL. In the pessimistic case, you certainly have time to get to Burbank Airport or the Hollywood Hills, right? We're still inside LA. You've now kind of surrounded Pasadena, right? I've gone a little bit too fast. The next fastest, I've got 2 options to offer, and I'm going to do a pop quiz. Which one of these do you think is faster? Local attached spinning disk or local area network attached SAN running NVMe SSDs? The SAN, yes, it is, and it's quite a bit faster. So SSD powered SAN, we're now up to hundreds of microseconds. It is another 5 times slower. So we now have, tens or hundreds of terabytes. We have storage arrays that can basically be arbitrarily large. But you're about halfway to San Diego at this point. Entire Los Angeles County is surrounded. You're now in like Santa Barbara, northwest, or you're in what's that town down there, Carlsbad in the south. You're quite a bit away, right? We're talking about 40, 50 miles. Next up, if I am using spinning disks, if I'm using SATA disks, how far, anyone want to care to wager how far, not wager, but guess, how far light can travel in the time it takes me to read from a spinning disk? Las Vegas? DC, New York? Who said New York? Who thinks New York is right? Who thinks Vegas is right? Yeah, you can get to Hawaii or New York. You can get to we're talking about. I could swear these slides were. Am I working on an old version? Anyway, we'll flow with it. We'll go with it. You can get to the Empire State Building easily, right? We're talking about 5 to 15 milliseconds of latency. So we're talking about another order of magnitude, right? Another 2 orders of magnitude so just the spinning disks, you have platters, you have a mechanical head that's seeking to read from a certain area. If you need to go to on-disk swap, for example, your performance takes a hammering. At this stage, the scales have gone from nanoseconds to microseconds to milliseconds. So by the time your data is loaded into your hard drive, light could have had the time to reach New York. And in terms of lessons learned from this, where you read your data from really matters. The closer your data is to the CPU, the faster your reads are. So you want small, fast, and close to the CPU for hot path data where performance is critical. And in terms of orders of magnitude, DRAM is 100 times slower than L1 cache. NVMe is 1,000 times slower than, is 1,000 times slower than DRAM? No, 1,000 times slower than L1 cache. And traditional hard drives are another 100 times slower than NVMe. So 100,000 times slower than reading from cache. That's a massive performance hit, right? If you have to read from disk, it's a performance killer. So what do you do with that information? How can you make sure that you're using algorithms and data structures that allow you to have that hot path data be efficiently used as part of your program? So designing hot data to fit in cache, processing large data sites in cache-sized chunks, using algorithms that allow you to do that, cache by chunk, that's going to be important for application performance if performance really matters, and we'll get to that a little bit later. Okay, next, let's move on to how data actually moves around inside your system. When you read a byte of data, you're not moving a byte of data into cache, right? The smallest unit of memory transfer is a cache line. I've used a carton of eggs here, but it's like, you don't move data byte by byte, you move data chunk by chunk. The minimum amount of data that gets moved around in cache is a cache line. Cache lines are 64 bytes. So when you read from a memory location, that memory location is first in RAM, right? If the data is actually on disk and needs to be loaded into RAM, it's going to be loaded into RAM. That's called a page fault. That's a slow operation. Once it's in RAM, you seek to the specific location where that memory that you care about is, and you look for the boundary-aligned 64-byte chunk of data, and that's what you read into your L2 and L1 cache. Why does that matter? A cache line is 64 bytes of memory, and if a cache line is in cache, reading it or any of its neighbors that are already in cache is essentially free. It's 1 nanosecond for access time versus 5 nanoseconds or 150 nanoseconds or a couple of microseconds. If a cache line is already in cache, if a cache line is not in cache, the whole line is read from DRAM before data is loaded. And the way that works is you have a memory controller on your CPU activates a line of RAM. You have the way RAM activation works is you've got a first operation, it finds what row. RAM is laid out as a 2D array of capacitors, basically. They're either capacitors are loaded, in which case it's a 1, or they're empty, in which case it's a 0. And it finds the right row. That operation has a certain cost, and then it finds the column inside the row where the cache line starts, and that operation has a smaller cost. So if the row is already open, you get an optimistic, like maybe 50 nanoseconds. If it's not open, then it costs about 150 nanoseconds to read from RAM. So your memory manager is also kind of smart. It looks at how your program is accessing memory, and if your access patterns are predictable, it will automatically read in lines that it expects you will need in the future. If you're wrong, that has a cost, right? You've loaded memory into RAM that then gets evicted and something else needs to be loaded in instead. What that means as a programmer is that cache lines are prefetched based on data access patterns, and predictable access patterns mean that you're going to be using that data more efficiently. If you do sequential access of memory across contiguous blocks of memory, then basically your average read time is going to be closer to 1 nanosecond than higher, right? And data structures really matter for this. If you're a C++ programmer, if you're using arrays or vectors, those are fast, those are contiguous data blocks. If you're using on C or C++ or really any language, kind of binary trees or linked lists, those data structures essentially jump randomly around in memory because you've got a pointer to the next thing is part of the data structure. And every single read of an element of a linked list is going to cause some kind of cache eviction and loading in a new line. So arrays and lists outperform linked lists or binary trees. Again, I'm not saying that you can't use or you shouldn't use those data structures. What I'm saying is if you're in an area where performance is critical, you want to make sure that you're optimally using all of the data that you load into cache. You want to make sure that every cache line you want to get 64 reads, right? You don't want to be reading one byte out of a 64 chunk and then reading another byte out of a 64 chunk and doing that over and over and over again. That's optimally poor performance. You want to get optimal performance, which means using that sequential data structure. So this is not just theoretical. Let's take one example. If you're doing image manipulation, I used to work on the GNU image manipulation program. Commonly in graphics programming, what you're going to have is the image is going to have 3 arrays, or 4 arrays, depending on how many color channels you're using, with an array for the red data, an array for the green data, an array for the blue data, and an array for an alpha data. The reason why we store it that way is because you can optimally do a lot of image manipulation algorithms by processing chunks of those data. You can do that SIMD because the data is laid out in memory already. You're just passing in a new address and you're adding 64, adding 64, adding 64, whatever. So game developers routinely store image data in an array per color channel because it allows them to efficiently process that data using SIMD. This is called, by the way, in the game world, this is called data swizzling. If you're looking for, if you want to look this up. So laying out data that you really care about the performance in these contiguous data structures is kind of something that's real life performance engineering. Okay, so we're going to check how much this matters, and it's going to be hopefully interactive again. I'm going to take I've generated 1 million entry matrices, 1024 by 1024. So an A matrix and a B matrix, we're going to multiply them together. So each entry in the C matrix is going to be a sum of AIK times BJK. So we're going to go across the rows of the matrix, and we're going to go down the rows of the second matrix. So this is what we're doing. We're multiplying 1024 by 1024 matrices. The code for this is super straightforward. This is too small for you to read, which is my fault. But the naive method goes for we're going to go for each ij in the C matrix. So we're going to traverse the C matrix row by row by row. For each entry in the C matrix, we're going to process a row of the A matrix and a column of the B matrix, right? So that's the naive method, is we go so the inner loop is K, which goes across a row and down a column. The second method we're going to use is column first. What that does is we're going to change the order. So instead of going across the C matrix first, we're going to do as our inner loop the column of the inner loop is going to be the column of the C matrix and the column of the A matrix. The outer loop is going to be our J, which is the column of the B matrix. Okay, and then the third, we're just going to change the order another way, and we're going to do row first. So we're going to change the order so that we do the row of the A matrix, the row of the B matrix, and the column of the C matrix. I'm messing this up, but. Like, the point is, the only thing that changes here is the order of the loops ijk. Okay? I was going to ask. So let's just jump in. The consequences for performance are dramatic. Ensuring that the inner loops are following row order for all of the major matrices, right, means that for each entry, so in the naive case, every element of the C matrix we're calculating it and then we're moving on to the next one. In that naive case, we were getting 126 seconds on a single Ampere 1 core. If I do the worst case, which is the column first, as much as I can, it's actually not that much slower. It's 146, 147 seconds. So those were both getting really hit by cache line loads, right? Because every single entry in the C matrix that I'm calculating is loading different cache lines every time I go down to a new row. If I changed if I only just change the order so that for each entry, for each member of the outer loop, I'm going across 2 rows. That's the only change I made, right? The numbers go down to 8 seconds total, right? So 126 or 146 to 8, that is a 20x time saver, right? This is a fairly simple mathematical operation, right? By the way, there are faster and better ways to multiply matrices, and we'll talk about those a little bit later. I reference them, but I'm not going to go into like tile-based matrix multiplication. But I will talk about that in terms of pointing you in the direction of places where you can learn more. So far from being a minor concern, this has a dramatic impact on the performance of something like matrix multiplication, which is key to, as we all know, AI, right? So this is the kind of thing where you really care about the performance of your application. So how you access data matters in addition to where you access the data from. Sequential access of contiguous data is fastest. Cache line misses and page faults can have a dramatic impact on application performance. And putting that into practice, you want to make sure that for the performance critical, and I'm kind of repeating this because we'll talk about premature optimization at the end, but for the performance critical aspects of your application, you want to make sure that you're using data structures with flat data types, so everything's the same size, so you're not doing arrays of structs that are contiguous in memory. And you want to access those data types sequentially to optimize for hardware prefetch so that your CPU memory management module can like make sure that data is ready for you when you need it.
Would another way of putting it, though, be how you access it changes where you access it?
How you access it does change where you access it. Indeed. Yes. So this gentleman said, isn't it like how you access it changes where you access it from? And that's correct, right? If you access data in a random manner, basically, you're going to be going to DRAM an awful lot, or disk, potentially. Okay, let's talk a little bit about modern CPU pipelines. It's possible to, modern CPU pipelines, there's process multiple instructions at the same time. So this may be old hat or knowledge that everybody here knows already, but instructions are loaded by the CPU into, I'm going to get in trouble here because I'm probably going to be wrong, but I think the ALU. So they're loaded from memory. Instructions that are loaded from memory are being loaded from iCache, which we saw earlier. That's 16 megabytes per core, 16 kilobytes per core, excuse me. In another stage, those instructions are decoded, so they're prepared for execution in terms of reading from registers that need to be read from. Then you've got the execution stage where the instruction is executed. Then you've got a memory stage. So if the instruction is a load or a store or requires some access to memory, memory access happens in stage 4. And this is a simplification. There are CPUs that have different pipelines. This is just kind of a standard RISC pipeline. And then in the 5th stage, you've got write back. So any results of that instruction are written back to registers so they're available. And then the instruction is retired. So optimally, you can have 5 instructions being processed at the same time in different stages. That's what's happening in the green column here. However, each one of these stages can stall, right? If you're reading instructions and the instruction is not available in iCache, then you can end up going to main memory to get the instruction that you can decode. And so you're going, instead of a 1 nanosecond read, it can be a 150 nanosecond read if your main memory is busy. Similarly, on memory writes or reads, if the memory is not available in your D-cache, then you're going to be going to main memory or disk, and that can be a very costly operation. So you can stall the CPU pipeline in a number of ways. And one of the ways is branch prediction. So some of you may have heard of branch prediction or in the context of Spectre and Meltdown. This was the side. This is what we call side channel attacks, right? Basically, you can access some kind of indicator to what would have been loaded in the branch predictor, so that you can see something that never actually happened, but that can reveal data about what's going on in the CPU. I don't fully understand it. I have several friends who understand it a lot more, but this is the mechanism that's used. Basically, modern CPUs are going to have, like any program is going to have branch points. You know, if this happens, then do this thing, otherwise do this other thing. And because what you're doing is essentially, you want to keep that pipeline full. You want to make sure that you're loading what's the next instruction that's going to execute. And inside the CPU, you have the branch prediction module. Basically says, oh, I see a branch coming up in 3 instructions time. Based on what I've seen in the past, I predict that this branch will be taken, and you load that instruction, and you're getting it into the start of the pipeline. Now, if by the time that branch instruction is actually being executed, your prediction is wrong, you throw away all of the work that you've done in preparing that instruction, in reading registers that are required, in getting it ready for execution. You throw all that away, and any other instruction that you've loaded after that, and you have to restart your pipeline. Oh, okay, I was wrong, branch misprediction, I throw everything away. What's the next instruction? I'm loading it from my cache. So the cost of the prediction, if it's wrong, can be up to 20 cycles. On an Ampere 1, we've got an average branch misprediction cost of 10 cycles, which is very impressive industry-wide. But branch predictors on current hardware can achieve 95 to 99% accuracy on typical workloads. And you will see some numbers in just a second. The predictor maintains a history of recent branch outcomes and basically is very good at predicting what comes next. So you want to keep that prediction success rate as high as possible. 99% up is what you're aiming for. However, programmers sometimes do stupid things. And the way that you code, the way that you code can make it more likely that you're going to have a branch misprediction. There are a few dependencies. There are a few things that happen in CPUs, right? You can have data dependencies where an n+1 instruction is calculating something that's needed by the n instruction, and you can't execute that n instruction until the calculation is completed. That stalls your pipeline at the execution stage. You can have control dependencies where the outcome of instruction n changes the instruction n+1 to be executed. Branch misprediction, we already talked about that. I'm not going to spend any more time on it. So here are some of the ways that developers can break your pipelines. If the CPU is pretty smart about branch prediction, what can I do about all this? Are there things that I do to make it better or worse? And you can definitely make it worse, right? 3 ways that the pipeline stalls. I've talked about back-end stalls. That's when you don't have memory that's required already in cache. You have front-end stalls. That's when your instruction that's required is not yet in iCache. That happens, for example, if you have a lot of functions. You don't necessarily think of a function call as a branch. It's a branch. You're going to a new part of memory. That can happen if you have, for example, if you have a C++ code with a lot of polymorphism. If you have multiple definitions of a function that are rendered at runtime, that's essentially something that the CPU can't predict, right? It doesn't know what the next instruction is based on what you've been doing in the past. So you can cause instruction cache misses with bad function etiquette, especially on the hot path. And branch misprediction, you can make it hard for the CPU to predict what comes next. And we're going to go into an example of some of the ways that one example of how you can make branch prediction difficult. But yeah, so if you have lots of small functions that are called through function pointers, if you have lots of polymorphism, if you have lots of, these are things that can cause higher branch misprediction rates. So here's one example. We're going to generate a list of 10 million random numbers between 0 and 100, floating point numbers. And we're going to count how many numbers are under 50. Right? If the number is under 50, add 1 to the count. If it's over 50, add 1 to the over 50 count. just to have a little bit more time, we're going to iterate that over that 20 times. So what you're going to see here is 20 times 10 million, 200 million. We have 200 million branch operations, and we're going to see how many successful predictions we have versus unsuccessful predictions. On the first time through, we're going to do it on random data, just straight out of like the random number generator. On the second time through, I'm going to sort the list and do exactly the same operation, right? It's the same code being run on two different data files, one where it's random, one where it's sorted. I'm going to use perf to count the time and the branch predictions for the operation. Okay, on the unsorted data, so I delay 500 milliseconds. That's just to allow the Python VM to start up, and I'm kind of not counting Python startup. I'm looking for how many cycles, instructions, branches, and branch misses I have. I'm going to pin this to a single core, just so that it doesn't move around. Like, I don't want the kernel to be doing anything smart. So what I get out of my count is, I don't know how many digits are in that. 3, 6, 9, 35 times 10 to the 9 cycles. I end up with, 2.5 instructions per cycle, which is, we were talking about you can execute up to 5 instructions per cycle. This is pretty awesome. Like 2.5 is pretty good. We end up with 100 million branch misses, which is 1.92% of all branches. There are, in general, and this is kind of expected, we're running Python, right? This is the full Python VM. There's a lot of code that happens before my code gets even processed. So we end up with, I don't even know how many, 5 by 10 to the 9, 5 billion branches, 100 million branch misses. But 100 million branch misses is kind of what we were expecting from our data, right? 200 million comparisons, we were expecting 100 million misses, 100 million hits. Basically, we're flipping a coin. We end up with our total time being 11.2 seconds user time for processing this list, right? So branch miss prediction, 100 million, time 11 seconds. On the sorted data, I do the exact same operation, but I'm running on a sorted data list. What happens is, the first time through, it sees something close to 0. Next time through, it's 0.2 or whatever. And it's like, oh, I predicted under 50 last time. I'm going to keep predicting under 50. And then it hits 50, and it gets it wrong once. Maybe it gets it wrong twice. And then it's like, oh, now we're over 50, and it just predicts over 50 every single time. So we've gone from 100 million branch misses to 2 million, which is pretty much what we would expect. We've gone from 11.2 seconds to 9.7 seconds. So on a relatively simple piece of code, we're saving a second and a half on this particular algorithm, not by changing the code, by changing the way that we feed the data into it. So this is all in Python. There's a reason I use Python and not C for this. I talked about how compilers are amazing, right? If you do the same thing with C, compiled with the right optimization level, it automatically detects there's an if-else, and it uses a branchless instruction. It will use a ternary instruction. It will use some kind of method to say, okay, I'm going to do a test, and then I'm going to, like, it uses an instruction which doesn't use a branch, right? Which the CPU can then read sequentially. So we get an identical result with and without the sorted data, just because the compiler is awesome. So some of this stuff that I'm introducing to you here, compilers do help you take care of it if you've got -03, -04. The way it does it is pretty neat, and it's worth dwelling on a second. The C compiler does better because it can avoid branch mispredictions by avoiding branches. So for those of you, who here has heard of branchless programming? Got 2, 3 folks? Okay. We can avoid branches altogether by using branchless algorithms or language constructs. Here are just two ways to eliminate the branch in what we just saw. One is a ternary operator, which gets translated into different assembly instructions. So you go x less than threshold, under plus plus, or over plus plus if it's greater than threshold. Or you can use bitwise arithmetic. You create a Boolean that is this data element is less than a threshold, and then you add the Boolean to both the under and the over. If it's less than the threshold, the under goes up by 1. If it's and the over doesn't change because the Boolean is false. If it's greater than the threshold, the under doesn't change because it's false, and the Boolean and the over goes up by 1. So there are a lot of branchless programming techniques. It's out of the scope of this talk. But if any of you have heard of the $1 billion challenge, anybody here for the $1 billion challenge? I recommend you go looking at it. Yeah, so something that came out of the Java community last year, I think. So there was a reference file of a billion rows, a billion row challenge, a reference file with temperatures from weather stations that had a billion rows of data in it. And you had to accomplish some task of the min, max, and average temperature for each weather station. And there was a kind of a reference implementation that was bog standard Java that took, I think, 140 seconds, right, to process the billion rows. And by the end of the competition, people had gotten it down to 3 seconds. The way they did that was some of the techniques were really interesting. It's just like we're going to load the data with a mem map and instead of reading rows. Some of the techniques are, we're going to skip the slow part of terminating the process. We're going to trick the program into ending the time, and then we'll do cleanup after. But the biggest gains were by moving to branchless processing of the data. So I strongly recommend you look at that. Branchless programming is a way to deliver maximum performance on the things where performance really matters. Sometimes, as a warning, some of the people I've talked about to this are like, yeah, but branchless code, sucks because it's hard to maintain, it's kind of confusing, and that can be true, right? If anybody who's seen John Carmack's inverse square root function, right? You know that like magic numbers kind of pop up out of nowhere, and you don't know what's going on. You're kind of casting an integer or a float into an integer, adding a magic number, or anding it with a magic number, and then casting it back to integer. Yes, there are sometimes situations where you're going to make your code harder to understand, harder to maintain. But if you really care about the performance of that thing, if it's a thing you're running billions of times per second, then you want to make it as fast as possible. Okay. Warning. Don't fix what's not broken. Before spending a ton of time fixing something that will only have a small effect, you need to do some profiling. So this is a graph generated from an Ampere tool called the Ampere PMU Profiler, which basically investigates CPU events using the PMU, Performance Monitoring Unit. And it can tell you where you're losing time. Are you losing time in the front end because your instruction cache is not being hit well enough? Are you losing time in the back end because your memory is not being consistently or efficiently accessed? Are you losing time in your pipeline? Make sure that you're using tools that are available, like Perf, like the Ampere tool suite, to see what's going on in your application. Before you invest a lot of time doing things like improving the performance of the idle loop, which is kind of the classic example of premature optimization. Okay, so lessons learned. You can make it hard for the computer to predict the future. You can help or hinder your CPU branch prediction. Try and get out of the way. Getting out of the way means that your CPU, you're basically taking advantage of all of the engineering that's gone into your CPU. Inefficient programming that leads to poor branch prediction can slow down your program. Using branchless techniques or algorithms algorithms is going to reduce branch misprediction. And if you're doing any high performance programming, if you're doing any GPU programming or SIMD, using SIMD modules on the CPU core, SIMD doesn't have branches. You're just processing bunches of data. So learning how to do things with bitmaps and processing data chunk by chunk has the benefit of automatically being branchless, right? So it does require learning some branchless techniques. Okay, we're running out of time fast, so I'm going to just zoom through developing for parallelism. Why is this important? The cloud has kind of changed how we develop code and how we develop applications. We now have dozens of services or applications. Each have their own components. Each are running on virtual machines that can have lots of compute, right? We talked about the Ampere 1, 192 cores. It doesn't make sense to run a single-threaded application on a 192 core machine. You're going to have one red hot core and 191 that are sitting idle doing nothing, right? So the cloud has fundamentally changed the way application development happens. So there are a few techniques that we can use to make sure that we're taking advantage of all of those cores that we have at our availability. Coding for more cores is different. And here are just some of the ways. There are a lot of them. I really like this Ian Coldwater. There are a lot of them. First is you're going to be running, if you're using in a single application many cores, you're going to be using threads. I like a joke where, you know, a programmer had a problem, so they used threads, now they have two problems. Threaded programming is hard because you end up needing to be careful about critical areas of our code where you've got information shared between threads, right? So you need to have the appropriate level of locking, you need to have the appropriate semantics around acquiring and releasing data. And you can do, you know, we'll talk about this in a second. You don't have to completely lock data so it's only one thread accessing the data, particularly if everybody's reading the data and you only need to update it when it writes, right? So having the right level of locking is important for performance. Parallelizable algorithms. So we talked about the matrix multiplication earlier. You can do tile-based multiplication of matrices, which means that you've got small cache-sized blocks of your matrices, A and B. In cache, you're generating a block, an intermediate block, and then at the end, once all of the intermediate blocks are available, you add those in a certain way and you get your matrix multiplication C. So having parallelizable algorithms means that you can ship little pieces of a problem to different cores and aggregate the results when they're done. But that results in data synchronization issues. You need to make sure that there's no data shared across different cores. You've got mesh congestion issues where if you're shipping a lot of data between different cores, you can gum up the system basically and add latencies to your mesh congestion. I haven't talked about, and I won't talk about beyond this, NUMA. So NUMA is, it stands for Non-Uniform Memory Access, thank you. So if you have multi-socket systems, each socket is going to have a fast track. I think I actually have a slide on this. Each socket is going to have a fast track to certain storage, memory, peripherals, right, network cards. If a CPU core on one NUMA node tries to connect to a network card on another NUMA node to do network reads, the latency is going to be terrible because it's not on the fast path. But the main thing I'm going to talk about here is cache coherency and false sharing. So I don't know, who here has ever heard of false sharing? One. Nice. Good. You're all going to learn something. Excellent. Before we get into cache coherency, I want to just give credit where credit is due. None of this is original material. This is Scott Myers, who is an old-timer programmer. I strongly recommend the presentation CPU Caches and Why You Care by Scott. He goes into this in a lot more detail than I'm going to. I'm going to give you a flavor of it. But there's way more, and I recommend that you look into everything that's involved in parallel programming, and I'm going to link to some resources in the slides that will be available for you afterwards. But let's talk about cache cohesion. When cache lines are loaded into the CPU cache, if you have two threads that are using, that load something into CPU cache, they're copies of the canonical reference data, which is in main memory, right? There is only one reference in main memory. Everything else is a copy. So if multiple cores are using the same cache line, writing in one core needs time to propagate to main memory and to the other copies of that. So let's look at what happens as it happens. Let's say we have two cores, core 0 and core 1, who are accessing the same cache line. I'm talking about cache line because, again, that's the atom of how memory moves around in the system. Core 0 and 1 both get a read-only copy. It's marked read-only. It's marked read-only and shared. If core 0 writes to the cache line, core 0's copy gets marked for synchronization. Core 1's copy gets marked as dirty, no longer up to date. So core 1's copy is now marked as invalid, and an invalidation message is sent to any other cores that are using the same cache line. Core 1 tries to read the line from memory, but is stalled until it updates the line from either core 0 or main memory. Both cache lines then return to this status shared, right? So basically, when I write here, I can't read here until that write gets propagated. And its cache line is the scope, and I'm emphasizing that because you'll see why in a second. So this, there's a kind of a seminal Dr. Dobbs article from, I think, 2008 or 2007, by this gentleman, Herb Sutter, who describes this problem of false sharing. He describes a scalability issue that he came across. So, again, the code on the right is unreadable. It doesn't actually matter. All we're going to do is we're going to take a task. We've got a large corpus of data. We want to count how many times something happens in that corpus of data. And what we're going to do is we're going to break that down into 16 chunks. We're going to send a chunk to different cores. We're going to count in each core how many times that thing happens. And then we're going to add up all the counts at the end, right? The way that we do that is we have an array with 16 entries, core 0, core 1. So count 0, count 1, count 2, count 3, up to count 16. And inside an inner loop, we're going to increment that counter every time we get a match on the thing we're counting for. So when you ran this on a 24-core machine, not a 16-core machine, but we're going to just run with it. On a 24-core machine, this is the performance he got, right? When he went from 1 core, reference 1.0 or 100%, to 2 cores, he actually lost 40% of the performance. This is not what you're looking for in scalable programming. It took until he started to gradually improve the performance as he threw more cores at it. It took until I think he gets to 16 cores before he's above 100%. So he's using 16 times as much compute, and he's generating what he could have done with 1 core. This is not good. And eventually, it gets to a point where performance starts to go down again when he gets to core 20, 21, 22, 23, 24. So this is, obviously something is wrong here. He made a change. Before we get into how he fixed it, we're going to make a small assumption. Our array of integers storing counts is stored in a single cache line. So here's what happens, right? We've got our main memory cache line with our 16 counters. Core 0 gets a copy, core 1 gets a copy. Core 0 finds a match somewhere in the corpus of data and writes its entry into entry 1 of the cache line. That marks the cache line dirty. Okay? At this point, core 1's cache line is out of date and is also marked dirty and needs to be updated with this new write. Okay, so at that point, the core 1 copy of the cache now gets marked stale until the core 0 write replicates. Core 1 has found a match and wants to update count 1. It wants to update the second entry in the array, and it can't do it because the cache line is dirty. So the cache line gets propagated, which takes a few milliseconds, I think. And then now core 1 can write to count 1. Okay, it's written to count 1, and that cache line gets marked dirty again. Now, note they were not writing to the same memory location. They're writing to 2 different entries in an array. But because those two different entries in an array are in the same cache line, it completely stalls the program. So they lose all of the benefit of having multiple cores thrown at the problem. You make a small change. Rather than using array entries, you have inside each thread, you create a local integer that's just account for that thread. After you've processed the chunk of data that's allocated to that thread, you set the array entry equal to the count that you end up with. Okay? By doing that, you've removed all of the intermediate writes. You're writing once per thread, so you're writing 16 times. All of those writes get synchronized. You add them up at the end when all of the threads complete, and you get the result. What Sutter found is that he went from what we saw earlier, that mess, to this, right? Adding 24 cores, he gets 24 times the performance. So what are the lessons to be learned from here? Be careful when you're sharing data across multiple cores. Attempting to modify a shared cache line on multiple cores will end badly. You need to have some awareness of any time you're sharing cache lines, because as we've seen, it's a massive performance killer. So it does need a little bit more care. So what can you do about it? We have some really good techniques that have developed over time for parallel programming, and they're common lessons from microservices, right? Consider functional programming best practices. So this is kind of, generally speaking, shared nothing, immutable data, pure functions. So a pure function is a function that when you call it, it has no side effects, and like any changes it makes are own. It's given a task, it does the task, it communicates with other functions through messages. There's no shared data. You can use perf C2C, which I really like, to see if there are more load hits on modified memory than you would expect. So this is basically analyzing cache line locks. So in general, thinking about, well, I thought I had something on memory. This may be in here. So part 4, conclusions and lesson learned. Where you read your data from matters, and how you access your data matters. You can make it hard for your CPU to predict the future, and you need to be really careful when sharing data across multiple cores. So those are the lessons learned. What can you do about it? Again, keep your hot path data, I'm going to be insisting on this, keep your hot path data small and contiguous, and process it in a contiguous sequential manner. Use your data structures with flat data types that are contiguous in memory. Access those data types sequentially to optimize for hardware prefetch. Avoid a lot of, I don't think this is in the list, but avoid a lot of things like function pointers that are dynamically rendered at runtime, or polymorphism, particularly in performance critical parts of your code. Use branchless techniques in inline code to reduce branch misprediction. Compilers can help you here. And functional programming techniques will help for parallel programming. And I want to particularly call out to memory oblivious, I think it's cache oblivious programming. Cache oblivious programming. So if you're getting into the world where you're programming for performance with multiple cores or multiple machines, cache oblivious programming is basically, this is a set of algorithms for common high performance tasks that allows you to operate locally on data. So you process data by chunks, you can do things in parallel. Obviously important for AI, and it's particularly important with generative AI because you've got multiple transformer layers, multiple attention heads, and all of the rest. But most important, do not optimize before you're ready, right? Measure twice, cut once. Benchmark and characterize your performance issues before you start making any major changes. The biggest changes are going to usually come from very simple changes, choosing the right algorithm, choosing good data structures. And that is it. And I've gone a little past an hour, but if I have the indulgence of the conference, I'm happy to stay for a few questions. And while we're taking questions, I'll put up first. This is some resources on where you can join the Ampere developer community. some information. We have an awful lot of information on performance engineering. We have a very, very high quality performance engineering team that communicates tuning guides about how to get the most out of your computer hardware, which is effective, which is both for like, it'll work on any architecture, but obviously particularly we give advice for ARM64. There's sample code, documentation, examples, and videos. We have a lot of information there, and I'm going to put up a list of resources at the end. So I'm happy to take questions.
I have the mic here for anyone who has a question. And let's thank Dave for a wonderful presentation. For any of you that still are attending the keynote, there is a keynote at 3 p.m. in Ballroom D and E. I'm coming around with the mic for questions.
Yeah. Thank you all for coming, and like I said, I'm happy to stay for a couple of minutes for questions, but if you need to go to the keynote or want to go to the keynote, you can leave right now. You don't feel like you're hurting my feelings.
Does Ampere have any custom ports of various like linear algebra libraries, like BLAS or anything like that, that's optimized for your
so
devices?
there is an Ampere performance, so we've got the Ampere AI optimized library, which is a set of optimizations for Ampere of PyTorch, Onyx, TensorFlow, Llama CPP. I'm not a... Are we recording?
Maybe I'm not AV.
Okay. Okay. I would like us to be...
You can take off the mic if you like, and everyone can move closer.
Yes, yeah, I'd be happy to answer that question later with a little bit more detail. I think, yeah, we do have some. Yes.
Anyone else for question?
You mentioned there's a piece of software, there's a PMU monitoring solution that Ampere
Yes.
has. What is it called?
You can see the link, it's not a link. Ampere Performance Toolkit. We have a set of 5 tools, one of which is only available to customers for reasons that I'm not sure what they are, but we have the Ampere Porting Advisor, which gets your code working quickly on ARM64 processors. It basically tells you which versions of your tool chains and where you might run into issues with dependencies. It even looks at code and says, oh, you're using this header and this library. Those are not available on ARM64. So that's the Ampere Porting Advisor. We have the Ampere System Profiler, which is a curated set of reports that we generate using standard performance tools, things like MPStat and perf. Then there's the Ampere PMU Profiler, which gives you those CPU level reports. And finally, we have the Ampere Performance Benchmarker, APB, which basically runs a set of curated micro profiling suites, benchmarking suites, and encapsulates, the important part is it encapsulates all of your system configuration in the report that it generates so that you can share that with somebody else and replicate a problem, which, like, replication of performance issues is kind of the #1 problem that our performance team has had. Like, a customer says, this is slow, and they're like, well, it looks fine to me. This is the tool that allows you to replicate a system configuration on another system and verify if you're seeing consistent performance. So those are the Ampere tools.
Thank you so much. Also, does it work on other ARM64 devices, or is it just...
Yes, they're all ARM64. They will work on every ARM64. And it's all open source, right? So it's on GitHub. Ampere Performance Toolkit, you can find it in the Ampere GitHub repository.
Thank you so much.
Thank you.
Anyone else for question? Anyone or comment or, you know?
Thank you very much. And thank you all for staying to the end. I'm going to let you all get to the keynote now. I've kept you long enough. Thank you.